Previous class we had studied about RS, that is the sheet resistance. This class let us study about CG, the gate capacitance. Okay, RS and CG are the very important parameters. How do you define the gate capacitance? It is defined as the gate to channel capacitance. Okay, it is the gate to channel capacitance of mass having W equals to L. Now, when we are talking about the gate capacitance, some standard values of these gate capacitance have been defined. What are those standard values? Let us consider for 5 micrometer technology. So, capacitance value is given as 4 into 10 to the power minus 4 picofarad per micrometer square. Okay, standard value. And you also need to know some standard values of different layers. As you know, MOS is stacked structure of different conducting and insulating layers. Their relative capacitance will also be different. So, let us first note what are the relative capacitances of different layers. First layer, gate channel. Gate channel, it is 1 Cg, and all these are for 5 micrometer technology. Next you have diffusion, 0.25 Cg, and you have polysilicon to substrate 0.1 Cg, and metal 1 to substrate 0.075 Cg. Okay. So, these are some standard values. You need to remember all these values. Let us take one example and see how to calculate the capacitance. Let us take one layer is given. Let the width be 3 lambda. This is the width, and the length be 30 lambda. Okay, this is a standard layer. He is asking us to calculate area capacitance. Okay, how do we do this? First, let us consider how to calculate if this is a metal layer. Let me say it is a metal to substrate. He has not told us which layer. I am showing for all the 3 layers whatever we had discussed earlier. First, let me say it is a metal to substrate capacitance. How do we find the capacitance? That is found by the formula relative area into relative capacitance. How do we find the relative area? Area, this is a rectangular block what you see. Okay, so it is length into width, that is 30 into 3 lambda. 30 lambda into 3 lambda divided by, I am talking relative area, means with respect to something I am going to verify this. What is that something? This is a standard 2 lambda by 2 lambda. This remains, denominator remains constant for all layers when you are calculating the relative area. This is relative area into relative capacitance is, I am talking about a metal to substrate. So, metal to substrate relative capacitance is 0.075 Cg. So, it is 0.075 Cg, and when you calculate all this you will be getting 1.6875 Cg. What is the value of Cg? Cg is 0.01 picofarad. This is in picofarad per micrometer, and Cg will be 0.01 picofarad, a standard Cg value. So, this will be 1.6875 into 0.01 picofarad, that is you calculate how much it comes to, that picofarad. Second, if I assume this layer to be a polysilicon, poly to substrate, then what happens? Again it is relative area into relative capacitance, correct? Relative area remains the same because it is the same layer under consideration. So, 30 by 3 lambda, 30 lambda divided by 3 lambda, and standard is 2 lambda by 2 lambda. But what is the relative capacitance now? I am talking about a poly to substrate. Poly to substrate, it is 0.1 Cg. So, into 0.1 Cg, that will come to some 2.25 Cg, that is 2.25 into 0.01 Cg, or sorry, picofarad. This is in Cg. You can keep it in Cg or you can convert it into picofarad. Next, if I consider this layer, whatever layer given here, to be a diffusion layer. So, if I say diffusion to substrate, then how do I calculate the capacitance? So, again it is relative area into relative capacitance. How much is the relative area? Relative area remains same because I am considering the same layer. So, it is 30 lambda by 3 lambda divided by 2 lambda by 2 lambda into how much is the relative capacitance? I am talking about diffusion. Diffusion, it is 0.25 Cg. So, into 0.25. So, this becomes 5.625 Cg. So, this will be 5.625 into 0.01 picofarad. Okay. So, like this, an example or a problem may be asked in the exam, wherein a layer will be given. They will ask you to find out the capacitance with respect to what kind of a layer it is, metal, poly or diffusion. Based on the type of the layer, you are supposed to select the relative capacitances to calculate what is the total amount of capacitance. Okay, we have some more problems which I will be posting in the next video. Next, we have what is termed as a delay unit. Delay unit, which is defined as tau. How do I define this delay unit? See, what do you understand by delay? If my input goes from 0 to 5 volts and I am trying to pass it through my NMOS transistor, at the output, if I say in the input it takes some t time, okay, for the input to rise from 0 to 5, output also it should take same time, but what happens is there may be a delay. It will not be a smooth transition from 0 to 5, it may be a delay like this. So, your output may take a longer time. It should have taken t, but it is taking a longer time due to stray capacitances. As I had told you, MOS is a stack like structure. You have different conducting and insulating layer, and you have insulator between these layers. So, these two layers between and you have insulator in between behaves like a capacitor. These are called as a stray capacitances. Depending on the size of the stray capacitances, delay will be more or less. That delay is shown as your tau. How do I define tau? Tau is defined as 1 Rs, okay, into 1 Cg seconds. It is calculated in seconds. So, 1 tau is equal to 1 Rs into 1 square Cg. So, with this I will stop for today. Rest I will be posting in the next video.